What the fuck?
RuPaul's Drag Race had fucked up drag.
I feel very attacked!
Hey, fake ass bitch. I don't like you, and you shouldn't even be here.
Hi, hello, and welcome to Queer Talk for the straight folk and everyone else in between and beyond. I didn't get in drag today because I'm lazy. But there's a little bit of makeup for you. A little bit of makeup for you to be happy. No, you're not happy? Sorry. So today's subject is going to be a little bit long, and thus I'm going to try to separate it into two parts. I want to talk about, I'm a scientist. Well, I'm not a scientist, like science. I studied chemistry in college, and so I have kind of a scientific basis, or let's say I have a scientific education, better said. And there are several subjects that I feel that are incredibly misunderstood about science in general, and that has a big repercussion. The social discourse and the debate, and everyone trying to, take little pieces of the scientific jargon to use it in a way that it's not meant to be, or try to justify bigotry through scientific jargon, and no. So what we're gonna do is separate the thing into two parts. First, I want to have like a real introduction into science and scientific terminology. Unfortunately, a lot of people still don't understand the difference between, for example, a hypothesis and a theory. When people talk about, well, that's hypothetical or that's theoretical, they think they both mean the same, and well, they don't. That's the point. Not to be a pedantic asshole or whatever, because I'm already over him. But if we're going to talk about science, if we're going to talk about something scientific, or we're going to discuss something that is scientific in nature, we need to respect the language. On the first part, we're going to try to, first of all, clarify a little bit those kind of terminology like theory, hypothesis, etc., that are a little bit blurry in the head of many people. And then we're going to see how this terminology and the way that we use this terminology and the methods that we use in science in general are what allow us finally to separate fact from belief or opinions or views. But what exactly is the difference between science and belief? And notice that I'm not restricting it to only religious beliefs. I'm trying to be as broad as I can to encompass all kinds of traditions, personal values, cultural things, or anything. This is one of the fundamental questions that we should ask ourselves before and every time that we approach a subject to learn it and to debate it. Why so? Because the answer to that question is factuality. Science does not concern itself with belief, because by definition, belief is something that doesn't need a proof to be argumented. And remember that something is a proof of something only if anybody can witness it, anybody can measure it or repeat it. If anyone can do it and get the same result as you did, then you can say that whatever it is that we're talking about is a science fact, is a scientific fact. But belief doesn't work like that. Belief is centered on personal perception and experience. To be a believer of something means not so much to rationally agree with the statement, but to empathize with the message. This doesn't mean, of course, that belief means to renounce the need or the desire to know why do things work the way they work. What it implies, though, is that the explanations we're looking for get an easy and complicated answer from our collection of personal experiences and collective narrative that we have created together with the people that believe the same thing that we do. That is not science. Those are views and opinions. And yes, both views and opinions are welcome into the scientific debate, but I think people have a severe misunderstanding of how that works, actually. Like, that is a problem because this is the corner store. Because that is the cornerstone of the debates on discrimination that we're having these days. One side is failing to recognize the majority of the talking points that they are using are about belief and not about science. And yes, for some people science doesn't have great value. I mean, just a couple of days, I'm sure that I'm not the only one who have seen people complaining about all the wasted money that we spend sending robots to Mars.
Teleport us to Mars!
But there will always be people failing to see the bigger picture. That is something that it's human. And if it's something that it's human, we shouldn't shun it, but try to resolve it. Anyway, the point is, science in itself, it has no agenda. I mean, the explanation why the sky is blue is not that the Democratic Party is playing the sun to emit the exact wavelength that is going to be dispersed in our atmosphere to create an eternal and continuous propaganda service for the Democratic Party. And I know what some of you might be thinking. Yes, this is valid for hard scientific facts. I mean, like physics, chemistry, math, etc. But the other sciences, those that we call social sciences, they are often seen as nothing but a philosophical discussion, nothing else. A simple exercise on ideology with a code of scientific rigor, but not real science. And I know this is true because, like I said, I studied chemistry in college, and this is an opinion that is often shared among peers in the nature science fields, which is sad. However, I doubt very much that we will still be treating them as sciences, at least in academic discussions, if the same scientific method that we use to explain the color of the sky or electromagnetism wasn't employed just the same and with the same rigor to social and cultural phenomena. But what is the scientific method anyway? To go back to a natural science example, because those are somehow easier, let's take two electrically charged particles and see what they do to each other. We find very quickly that if both particles have the same charge, for instance, if both are positive, they will repel each other. And if they are both opposite charged, they will attract each other. Not only that, but we can also measure the strength of that attraction or repulsion. And we can see that it always follows the same mathematical equation. We can vary the nature or the amount of the matter that we have in an experiment, but that won't change the effect. We can even change the temperature or the atmospheric pressure, basically anything, and we will always find that equal charges repel and opposite attract. Repeating the experiment and changing not only the variables of the system but also the person doing the experiment and the equipment for the measuring is the first step of the scientific method, because we need to know what depends on what and how much, but also we need to do it in a way that everybody can agree on and everybody can repeat it. Notice, however, how we still haven't given any sort of explanation for that attraction and repulsion. We've just observed something. It's a fact, something that anybody can measure and anybody can repeat. This is what we will call an empirical result, an observation that we were looking for, but that we've got now, and we need to find an explanation to it. And this is when the next step comes in, making hypotheses. When we have enough observations and data, meaning when we have enough facts that are verified and agreed upon by everybody in the field, we can use that collective knowledge to try to find patterns, trends, or any other particular aspect of that system to propose a logical explanation to what we're seeing. In our example on electrostatic interactions, we need to find an explanation that fits the fact that two positive charges will always repel regardless of their nature or how massive they are. So any idea we want to explore, we must do it in agreement with the observation that we can make. We call these ideas for an explanation a hypothesis, and that's what really means, at least in the scientific context, when people say hypothetical. For example, when we first studied the forces between two charges, some scientists proposed the hypothesis of an electric fluid within each and every substance, an explanation that looked entirely logical 4 centuries ago, but no matter how hard we have tried, we have never found such a thing. Not only that, but the more experiments that we did, the more we started to realize things like, for example, this force seems to be acting at a distance like gravity. So maybe the same hypothesis that we use for gravity, the gravitational field, we can use it for this one as well. So we can talk about an electric field as a hypothetical something that is around a charged particle that will allow it to interact with another charged particle. We didn't come up with this hypothesis out of nowhere. It's just that we see that this force acts like gravity, and if we think that gravity acts this way, well, maybe this force also acts this way. The only way to know is to experiment. And that's what we do. We make experiments. And what do we get out of those experiments? Well, we get observations that confirm, or that seem to confirm, the presence of an electric field, because some Newtonian laws make sense to be conserved in the way that we see it if the field is there. For example, like conservation of momenta and stuff like that. And not only that, but in those experiments, we can even see something like a field. We can see the electric field with the lines of force and everything. So you see, this, together with a lot of other deep theoretical things that of course I'm not going to explain right now, but this, together with a lot of other stuff, is what allows us to compare both hypotheses, the electric fluid ones and the electric fields one, and well, the data fits very well here. And here we have never found an electric fluid. So what we do is, well, we discard the hypotheses that have absolutely no proof of it at all. Why? Because we can test it, and we can prove it, and we can try to go even beyond. Or in other words, a hypothesis without proof is nothing but a dream, folks. Or a conspiracy theory. But this is not the end though, because we say the T word. You see, now we have an explanation to why electric charges attract or repel each other. Okay, well, there's an electric field and it allows electric particles to interact and to attract or repel each other. Okay, but why? What is an electric field? Why is it there? Who put it there? Where does it come from? Why? Our hypothesis, the one that we have confirmed and verified experimentally, has created a bunch of other questions. So we need now to find an explanation to all of those new questions. Science is a never-ending reiterative process where for each step that you take forward, you need to take 2 steps back, because you need to always confirm and guarantee that whatever you're saying is accurate, is rigorous, and is reproducible. Or in other words, the scientific method applies not only to the natural phenomena that we're trying to study, but also to itself, as it should. And doing this is truly, truly vital. Not only because of the scientific rigor that I'm talking about, like, okay, you guarantee that this result is the real result, but also because this is what allows us actually to get new insight into a particular system. where we can find relations that we hadn't noticed or we couldn't notice before because we didn't have the equipment or the knowledge. For example, it took us a while to understand that electricity and magnetism are actually two sides of the same coin. So that means that any hypothesis that we have postulated so far that contradicts this fact that we have verified now must be discarded or revised. So frequently, one hypothesis will create hundreds and hundreds of new hypotheses more, because unlike belief, there are no simple or final answers in science. There will always be more to understand or to explain. And I mean it, truthfully. We still have questions even for the most basic and normal things that we usually think of as absolutes, like numbers. We still have a lot of questions about them. That is the way that scientific progress is made, through testing, retesting, and challenging of new and old hypotheses. We don't care. We're gonna question everything. When we collect all of those hypotheses that we have verified or partially verified into a bundle of explanations relating all of the different phenomena that we have seen, that we have measured, and all of the reasoning behind, we can take the highest and the most difficult of scientific endeavors, postulating a theory. This is what we call making a model. And that means usually coming up with a mathematical or any other numerical way to input variables and to make predictions based on those variables. It sounds a little bit ethereal, so let's try to grind it down again. The charged particles that we have been speaking of this whole time. The attraction and repulsion of those particles is actually explained through the theory of electromagnetism, which is a collection of proven hypotheses that will not always give us the explanation to why charges interact in that way, but it will also give us the power to predict through the mathematical relationships that we have experimentally verified. So what that means is that even though scientists have not tested the force between each and every single charged particle in the universe, we have done it enough to have a mathematical equation that will allow us to understand that, well, I mean, if my first charge is like this and the other one is like this, how much attraction or repulsion will I get? Those kind of relationships sometimes get called a law. Not always, that's a little bit trickier. Thing is that the theory of electromagnetism gives us an explanation. I'm not going to go into that explanation. You can check SciShow or something like that to know that, to understand that. But the point is that electromagnetism, the theory of electromagnetism, which is a collection of hypotheses that we have confirmed or that we take as fact because we have done so many experiments about it, will allow us to basically predict the behavior of any two charges, no matter what they are, no matter where they are. And the better the theory is, the more extreme scenarios it will endure. I mean, if a theory is solid, there should be a way to explain through it anything related to a phenomenon. For example, electromagnetism. The theory of electromagnetism should be able to explain anything, absolutely anything involving electric or magnetic phenomena. And well, our current understanding of electromagnetism explains pretty well, really well. It could be actually the best theory that we have, the best and more exact theory that we have ever found. So, when we're speaking theoretically, in a scientific context at least, what we mean is that we are extrapolating our current understanding of something that we haven't studied yet, we haven't tested it yet, but that the theory meaning the collective knowledge that we have accumulated and verified and agreed upon tells us that something is possible or is impossible, or might be possible. Depends on what we're talking about. For example, the theory of relativity that was postulated by Einstein, when it was postulated, black holes were only theoretical, meaning that the theory says that they should exist. They could exist. And if you do the maths, you find that in some scenarios, they should be there. But we hadn't seen them. We have no proof of them. So they are nothing but theoretical things that are part of the theory, but we have no proof of them until we got it. We got it not only once, but we got it like several times. We have a mountain of proof that says black holes exist. So they are no longer theoretical, they are fact. They are a fact of nature, and they are part of the theory of relativity, because the theory of relativity has an explanation for them. They are not there because relativity says they have to be there. They're just there. And we have been lucky enough to have a theory, to have found a theory that allows us to have an explanation for them. But they have always been there. Always. So you see, theory is a way that scientists can utilize to justify new hypotheses. Or in other words, the sum of all the collective knowledge proven about a subject is what allows us to think about the causes of that something. Any other way to try to explain it is not science, it's belief. It's faith, basically. So, to summarize this very important introduction, let's remember always that an hypothesis, or a hypothesis, I never know if it's an hypothesis or a hypothesis. If somebody can correct me, I will be very glad. I live in France, so I don't speak English every day. But anyway, let's remember always that a hypothesis is an idea. It's an explanation that still hasn't been universally confirmed, whereas a theory is a collection of already proven or accepted hypotheses that give us tools and models to predict a phenomenon and to make new and better hypotheses. If you can imagine it, theories are like a skyscraper made out of thousands of individual hypothetical bricks, which means that losing or gaining one single brick doesn't mean having to tear down the whole structure. You can, just add or take away from it without the whole building going down. And this is something incredibly important to understand, because just witnessing something or seeing something happen doesn't mean that it will happen again. It doesn't mean that we understand why it happens, and it doesn't mean that anyone involved in that phenomena always do it the same way. If we only have one example, if we have only seen it once, then we have absolutely no scientific way to understand or to conclude anything about it. But okay, what does all of this have to do with homophobia and transphobia? Well, a lot in my opinion. But we're gonna have to wait until part 2 for that. I've spoken too much and my throat is acting a bit right. But until then, please just take care, try to be kind to everybody, don't be mean, and if you like and enjoy these kind of really long videos that I make about this kind of subjects, please like and subscribe, because that's the only way that the video is going to get traction, and the people that need to hear these things or need to get some clarifications about these kind of subjects will never get the message if we don't reach out to them. And I think that that's what we should. like I said, if it's a human thing, we shouldn't shun it. We should solve it. Oh well. Anyway, bye, Felicia.